What's up, stargazers? Welcome back to the Top 5 Countdown, your ultimate unit recap. I'm Caroline, and today we're helping you prepare for your unit assessment by counting down the biggest discoveries from this unit. Along the way, we'll discuss viewer questions that students just like you have sent in. Let's get this countdown started and see if we can uncover the answers. Coming in at number 5, Kepler's discovery that planets do not orbit in perfect circles. For centuries, people assumed planets moved in perfect circles, but Kepler's first law showed they actually follow elliptical orbits. Since planets orbit in an ellipse, their distance from the sun changes over time. This discovery helped explain why planets speed up and slow down as they move. Understanding elliptical orbits allows scientists to predict planetary motion accurately. This is crucial for space missions and satellite navigation. Speaking of satellites, we've received a viewer question about this topic. Felix from Florida writes, "Do satellites follow elliptical orbits like planets?" What do you think? Pause the video for a moment and make a prediction. There's actually multiple types of satellites. A satellite is any object that orbits a planet or star due to gravitational pull. This means the moon is a natural satellite of Earth. However, there are also man-made satellites, like the Hubble Space Telescope. Both types of satellites follow the same physical laws, and both follow Kepler's laws, just like planets. So, Felix, the answer to your question is yes. Satellites have elliptical orbits. However, the paths of man-made satellites can be adjusted with thrusters. This allows them to be maneuvered to correct their orbits, making their paths more flexible than planets or natural satellites. That's all for this topic. Let's see what's next on the countdown. At number 4 on the countdown, remember when we learned that there were 2 different views of gravity? Isaac Newton saw gravity as a force pulling objects together. However, Albert Einstein argued that gravity was not a force. He described it as the warping of space-time by massive objects. Both views of gravity are useful. Newton's law of universal gravitation works for most situations, but Einstein's theory is needed for extreme cases like black holes. Modern technology depends on both. GPS satellites correct for time dilation using Einstein's theory, while Newton's laws help launch them. Let's look at a viewer question on this topic. Kai from Kentucky asks, if mass creates gravity, does that mean even tiny objects like people create a gravitational pull? That's a good question. What do you think? Every object with mass pulls on every other object with mass, even people. Right now, you and everything around you are exerting a tiny gravitational pull on each other. But gravity depends on both mass and distance. People and most of the things around us have very small masses compared to planets. The gravitational force between 2 people is so weak that we don't notice it. On the other hand, Earth is huge, so its gravity completely dominates, keeping us on the ground. If you wanted to actually feel the gravitational pull between you and another person, you need to be much more massive. Like a planet. Now let's keep going and see what topic came in at number 3. It's time for number 3 on our countdown. Do you remember when we discussed how fusion could be the future of energy? Fusion is the process that powers the sun, producing energy by fusing hydrogen into helium. Unlike fission, fusion doesn't produce long-term radioactive waste and uses hydrogen, an abundant fuel source. But for fusion to work on Earth, temperatures must reach over 100 million degrees Celsius, far hotter than the sun's core. Scientists use magnetic fields to contain the plasma, but maintaining stable fusion remains a challenge. If successful, fusion could provide a nearly limitless clean energy source for the future. I wonder what viewer questions we got for this topic. Amara from Arizona asks, if fusion creates new elements, is that how all elements in the universe were made? Well, not all elements in the universe were made by fusion, but fusion played a major role in creating many of them. Fusion inside stars creates elements up to iron by fusing lighter nuclei into heavier ones. However, some elements need even more energy to form, which fusion alone can't provide. Elements heavier than iron, like gold, uranium, and lead, are created during supernova explosions or when neutron stars collide. So while fusion is responsible for building many of the elements around us, the heaviest ones were formed in violent cosmic events. We'll learn even more about that in the next unit. We're down to the final two. Let's see what's next. At number 2, who could forget when we saw light sneak through cosmic dust? Dust blocks visible light, but not infrared. Using infrared light allows astronomers to see hidden objects in space. Infrared telescopes, like the James Webb Space Telescope, reveal young stars forming inside nebula, which would otherwise be invisible. By combining infrared with visible and ultraviolet light, astronomers get a complete picture of a star's formation, life, and surroundings. Jordan from Oregon sent us a great question about this topic. Why does dust block some types of light, but not others? To answer this, let's think about how light interacts with objects. When light encounters something, a few things can happen. It can bounce off or scatter, get absorbed, or pass through. But what happens depends on the size of the object compared to the light's wavelength. So, how should we answer Jordan's question? Pause the video and make a prediction. Dust blocks some types of light, but not others, because they are different wavelengths. Dust is similar in size to visible wavelengths, causing scattering. But infrared light has longer wavelengths, so it passes through dust instead of bouncing off. Well, the big moment is now here. It's finally arrived. What do you think has claimed our number 1 spot? I present this unit's countdown winner. Spectroscopy was used to reveal stars are mostly hydrogen. This overturned early beliefs that stars were similar in composition to Earth. It's amazing how much information we get from light. That's because each element absorbs or emits specific wavelengths, creating a unique spectral fingerprint. By analyzing these patterns, astronomers can determine a star's composition. Today, spectroscopy remains one of the most powerful tools in astronomy, helping us unlock the secrets of stars, galaxies, and even the early universe. Let's look at our final viewer question from Han in New Hampshire. It reads, have we ever found water on exoplanets using spectroscopy? What do you think? The answer is yes. Astronomers have detected water vapor on multiple exoplanets using spectroscopy. Water has a unique spectral fingerprint, allowing scientists to identify it in a planet's atmosphere by analyzing the way light passes through. We've recently confirmed water vapor on a gas giant exoplanet. Water has also been found on smaller rocky exoplanets, though we don't know yet if it exists as liquid water. Finding water doesn't guarantee habitability, but that's an exciting clue in the search for planets that might support life. That brings us to the end of our top 5 countdown for this unit. Remember, there's a unit assessment at the end of this lesson. Be sure to check out the lesson activities to help you review and prepare. You can also go back and review any of the other lesson videos. I'll see you in our next unit.